Okay, so we are nearing the end of the energy unit. So the test over that's going to be after Thanksgiving break, and no, it will not be on Monday,
Yes.
okay?
We'll be on Tuesday.
I am cruel, but I'm not that cruel. Thought about it, don't get me wrong.
It's Friday though.
So, here's the
Or
story.
just cold.
What?
So you can have what we call elastic collisions, sometimes they're referred to as perfectly elastic collisions, and then you can have inelastic collisions. So if you have, and you would have to be specifically told this, if you have a perfectly elastic collision, what that means is that you lose no momentum, and momentum is the easier side of this, because momentum is a one-trick pony, okay? You have momentum, there's no other forms momentum can take. Yeah, you can have angular momentum, but all of this we're gonna be dealing with linear momentum. So it isn't like I can change linear momentum into something else, okay, like sound or light. Okay, momentum is a one-trick pony. It's a good trick, but it's a one-trick pony. Now, unfortunately with energy, energy can take on a whole bunch of different forms. So as this thing rolls, you can have some energy loss to friction. When the spring hits and bounces, hey, we're gonna make stuff move inside the spring, stuff being atoms. You're going to hear the spring, okay? So you're going to lose some energy to sound. So if you lose energy to any other form, sound, light, heat, the collision itself, distorting the bonds that hold the atoms together, if you lose energy to anything else, it's not a perfectly elastic collision because the energy is still there, it's just not mechanical energy. Now, I'm going to go through and I'm going to show you this derivation. Don't write it down. I'm not even going to do the whole thing because it would take you like 15 minutes to come up with the entire thing. I'm just going to show you the beginnings of this derived equation, okay? But it's going to show you kind of where we're going to go. So here's the story. I want to start with the energy side first because that's a little bit more complicated. So typically on these problems, you have what we call a target and you have a bullet, okay? You have something moving, you have something at rest. So you start off and you go the kinetic energy of the target plus the kinetic energy of the bullet equals the new kinetic energy of the target plus the new kinetic energy of the bullet. Okay, old school way, okay? Just like we've always done before. The sum of the kinetic energies before has to equal the sum of the kinetic energies afterwards. That's it. Now, this gets a little bit complicated. So that's going to be 1/2 mass of the target times the initial velocity of the target squared plus 1/2 times the mass of the bullet times the initial velocity of the bullet squared. And this is why this becomes quite laborious, because this is the mass of the target and the new velocity of the target squared plus 1/2 mass of the bullet times the new velocity of the bullet squared. And it's also very easy to lose track of variables because you have masses and you have all this other stuff. Now, conveniently at this point, what can I get rid of?
1/2.
I can get rid of the 1/2. So I can multiply everything by 2, that makes it a little bit more manageable, okay? Now, the next thing I want to do is that I want to get all the bullets on one side and all the targets on the other, okay? So I've multiplied by 2, all my fractions are gone. So, I'm going to come over here and go, okay, this is going to be the mass of the bullet times the initial velocity of the bullet squared minus the mass of the bullet times the new velocity of the bullet squared equals the mass of the target times the new velocity of the target squared minus mass of the target times the original velocity of the target squared. Cool with this?
Yes.
Good. Now,
Cancel
can I
everything.
factor out a mass?
Yes.
Yeah.
Yes. Cool with this, right? So I can write this as the mass of the bullet times the original velocity of the bullet squared minus the new velocity of the bullet squared equals the mass of the target times the new velocity of the target squared minus the original velocity of the target squared. Okay? Cool. Now, all of you are math nerds. If I ask you to calculate, hold on, Reed, that's a little misleading. I put that bracket in the wrong place. Okay? Same thing over here. So if I ask you to factor x squared minus 9, what would you write?
X plus 9 times quantity x times 3. No?
X plus 9?
Oh, wait, x plus 3.
X plus 3, x minus 3.
Did I say 9?
Yes.
He wrote 9.
So the quantity x plus 3 times quantity x minus 3, right? When you have the difference of squares. True?
It's not okay.
Is this the distance, is this the difference of squares?
Sure.
Yes.
Can we do the same thing?
Absolutely. Sure.
Absolutely. Okay? Absolutely we can. So we're gonna come over here and leaving out the 9 gap, Sean. I'm gonna have the mass of the bullet times the initial velocity of the bullet plus the new velocity of the bullet times the original velocity of the bullet minus the new velocity of the bullet. Cool? Difference of squares. Everybody cool with what I did? Now, I'm going to do the same thing over here. Whereas the mass of the target, new velocity of the target, plus the original velocity of the target, and then the new velocity of the target minus the original velocity of the target. Cool there, okay? Now, at this point, I'm just going to leave this here for a second, okay? We're going to revisit it, okay? I just needed to get it to that point. But you see what we got going here, okay? So we started, we said, hey, the momentum has to be conserved. We can get rid of the halves. We have a difference of squares. We can factor stuff out. Here we go. Okay. The momentum is easier because this is just the momentum of the bullet plus the new momentum, or plus the momentum of the target equals the new momentum of the bullet plus the new momentum of the target. This is easier because we don't have to worry about squares, okay? So this is just the mass of the bullet times the velocity of the bullet plus the mass of the target, new velocity of the target, mass of the bullet, new velocity of the bullet, mass of the target, new velocity of the target. Now I'm going to do the same thing what we did before, okay? I'm going to move stuff over and I'm going to factor this out. So I'm going to do this all in one step. So this is going to be the mass of the bullet times the velocity of the bullet minus the new velocity of the bullet, okay? And that's going to equal the mass of the target times the new velocity of the target minus the original velocity of the target. Everybody cool with what I just did? Okay? Now, because of the fact that you have to work with both systems at the same time, because both momentum and energy have to be conserved. So what I'm going to do is I'm going to take this line up here, okay, and I'm going to divide it by the momentum line, okay? There's rationale for this. So I'm going to take this, and I'm going to divide by, change up that color a little bit. So I'm going to divide by the momentum line. Mass of the bullet times the velocity of the bullet minus the new velocity of the bullet equals the mass of the target times the new velocity of the target minus the original velocity of the target. Okay? Now, conveniently, here's what's going to happen. The mass of the bullet's going to cancel out. Mass of the target's going to cancel out.
So the mass becomes irrelevant?
Initially. Okay. It doesn't later on. So then, here's the other thing that's going to happen, is that if you look at what's going to happen now, I can drop out some other quantities as well. So at this point, here's what I have left, is that, I've lost track of where I'm at. Here we go. Yeah, good. I'm where we should be. Velocity of the bullet plus the new velocity of the bullet equals the velocity of the target plus the new velocity of the target. Now, this simplifies down. At this point, you have to do some other substitutions, which literally takes an entire another page of substitutions. But here's a little self-check that you can do, and this is going to be important, is that if this is a perfectly elastic collisions, the sum of the velocities of the bullets have to equal the sum of the velocities of the targets. Okay? So if this plays out, this isn't the full equation, but it's a little like self-check. So if this is a perfectly elastic collision, the velocities here have to add up to the velocities over there. Now, typically, what do you think the original velocity of the target is?
Zero.
Zero, okay? That's, unless I tell you specifically, which I'm not, this is just gonna be zero. So what that means is that the velocities of the bullets have to add up to the new velocity of the target, okay? So that's a little check that we can do. Now, do not write this down. I will always give this to you. Do not memorize. Cohen, what are you looking at?
Nothing.
Oh. No. That wasn't your phone.
It was.
Oh, wait, I'm the only one too?
And you're the only one staring at your phone on your leg like no one's going to see.
Yeah, he just looks at his leg normally all the time, so.
That got you coal in your stocking from Santa.
Ooh.
Okay. So here's this next big equation. Do not write this down. I will always give this to you, because then you have to do a whole bunch of stuff to get to this. Mass of the bullet minus the mass of the target. Oh, let's get that out. Okay. This is the heart and soul of where you end up. Now, let's look at the mathematical ramifications of this, okay? So this is the new velocity of the bullet, this is the new velocity of the target. So let's start with this. This is the mass of the bullet times the velocity of the bullet. What do you get when you take the mass of the bullet times the velocity of the bullet?
Momentum.
Momentum. Okay, so this is basically saying, hey, we're gonna double the momentum. That's it, okay? Now, you're gonna divide by the sum of the masses. So the units have to work out. So I got mass divided by mass, that's cool. You're left with
Velocity, velocity.
velocity, okay? So that's the simpler one. Now, this other one up here, let's talk about this. So this is the new velocity of the bullet after the collision. So there's three scenarios that you can have. You can have a big bullet and a small target. You could have the mass of the bullet and the mass of the target being the same value. Or you could have a small bullet, large target. Okay? Cool with that. Now, let's start kind of in the reverse order. If you have a small bullet hitting a large target, what's going to be the sign of that difference in momentums? Excuse me, difference in masses?
Negative.
Negative. Original velocity of the bullet is always going to be a positive number. So if you have a small bullet hitting a large target, what's the bullet going to do? Well, it's going to bounce back. Okay? So this is what happened when Rutherford shot the alpha particle, which is just that helium nucleus, at that big massive gold nucleus. Okay? That's what happened. That's why that was a perfectly elastic collision. Because it came in, it hit that, boom, bounced back. Okay? So it's possible for the bullet to end up with a negative velocity means that it changed direction. Okay. What if the mass of the bullet and the mass of the target are the exact same?
0.
Zero, means what?
It just hits the thing and stops.
It just stops.
Is that like
And what that means then is that the target is going to leave with the same energy, the same momentum, everything that the target
Is
has.
that like a Newton cradle?
Same idea. So one comes in, boom, perfectly stops, other thing goes flies off. Now, if the bullet is bigger than the target, then what's going to happen?
It's gonna move with the target. No.
What did you say, Preston?
It's gonna move like with the target.
Yeah, because then what's going to be the new velocity of the bullet? Just the sign.
Positive.
Still going to be a positive value. Now, is the bullet going to slow down?
Yeah.
Yeah.
Yeah, because it's going to transfer some of that energy and some of that momentum to the target. So, stop yonder camera. Let's go to the back and see what that looks like.